Okay, so for this example, what we're going to do is we're going to pick the correct substitution based on the constants and the form that you see here. So first of all, what you need to do is convince yourself that we actually have one of these forms. Recall that what we're looking for is the square root of something, and you don't really see necessarily a square root. But notice that there's a 3/2. Notice this expression 4 minus x squared is raised to the 3/2. So if I were to rewrite that, what I would see is 4 minus x squared square root of 4 minus x squared. And that's where you can see the square root occurs. I mean, in fact, for that matter, if the denominator had been 4 minus x squared squared, I could have written this as square root of 4 minus x squared to the fourth. So there are situations where you don't even really see a fractional exponent or a radical, and you can still say that this square root of constant minus x squared does appear. So here we clearly have it once you understand the denominator in this way. So what we want to do is notice that this is constant minus minus a term with x squared. Let's go back to this slide. What you can see is that when I have constant minus something involving x squared, I want to use a sign type of substitution. So let's look at this. Let's look at 4 minus x squared. In this expression, if we're trying to map this onto a squared minus b squared x squared, then what we would clearly say is that let's write it out, a squared equals 4 and b squared equals 1, which implies that a equals 2 and b equals 1. So there I go. There I have what I need to do the substitution. So we want to use the substitution x equals b over a sine theta. So that's going to give us b over a is 2 over 1. So that's 2 sine theta. So we have, let's just put them together here. X equals 2 sine theta. There we go. Okay, so if x equals 2 sine theta, then we can rewrite this as, not rewrite, but we can continue with dx is equal to 2 cosine theta d theta. So that gives us that the integral of x squared dx over 4 minus x squared to the 3/2 is equal to the integral of x. So if x is 2 sine theta, then that means that we have 2 sine theta squared. You cannot forget about this dx here. You can't just ignore it. It's part of the integral and we need to deal with it in some way. So we know that dx equals 2 cosine theta d theta, so I'm going to multiply by 2 cosine theta d theta. So just to be clear what I have here, this term is x squared and this term is dx. That's where they fit into the original integral. So now I've got down here, I have 4 minus x squared is going to be 2 sine theta squared, and I'm going to raise that to the 3/2. Okay, so let's simplify this a little bit more. This is going to be, we have here 2 sine theta squared gives us 4 sine squared theta, and then times 2 cosine theta d theta, and then down here we have 4 minus 4 sine squared theta to the 3/2. Alright, so we want to continue to simplify. On top we're going to get 8 sine squared theta cosine theta d theta, and on the bottom what I want to do is pull out a factor of 4. So I have 4 times 1 minus sine squared theta to the 3/2. That whole thing rather goes to the 3/2. So let's continue to simplify. This is going to be 8 sine squared theta cosine theta d theta over, this is going to be 4 cosine squared theta to the 3/2. In other words, I just replaced that 1 minus sine squared with cosine squared, and this now becomes 8 sine squared theta cosine theta d theta over, this is going to be 4 to the 3/2 times cosine squared theta to the 3/2. We know that we can do that. We can break that up because of one of the laws of exponents that says that ab to the x equals a to the x, b to the x. So I just used that rule to do that. Okay, let's do one more simplification. Actually, I think we have two more to do. Tan squared theta cosine theta d theta over, this is going to be 8, and cosine squared to the 3 halves is going to be cosine cubed. There we go. All right, so we have the 8's cancel, and this is going to give us sine squared theta cosine theta d theta over cosine cubed theta. And that means that I can now cancel 1 power of cosine, turning this into cosine squared. So that's going to give us the integral of sine squared theta over cosine squared theta d theta, which equals the integral of tan squared theta d theta. Okay, so how do you integrate tan squared? Well, with tan squared, we know that tan squared, we don't know the integral of tan squared, but we do know the integral of secant squared. So fortunately, we have this really easy way to convert between tangents and secants, because tan squared is equal to secant squared minus 1. So that's going to equal just tan theta minus theta. There's the integral of secant squared minus 1 is just tan theta minus theta. Okay, so we now have, I'm going to draw the triangle. So we use the substitution. We use the substitution x equals 2 sine theta. So if x equals 2 sine theta, then x over 2 is equal to sine theta. So that means that the ratio of the opposite to the hypotenuse is x over 2, giving us a third side of 2 squared, which is 4 minus x squared. There we go. So what we can see is that therefore tan of theta, tan theta is equal to x over the square root of 4 minus x squared, and theta itself, we can read it really right off of that expression. If x over 2 equals sine theta, then theta is equal to the arcsine of x over 2. So that means that this integral is going to equal x over the square root of 4 minus x squared, and then minus arcsine of x over 2, and of course the hardest part of the problem, the plus c. So there we go. That's how you evaluate the integral x squared dx over square root over 4 minus x squared to the 3 halves.